Hi everyone, today I will tell you a story. Let's take a journey back to June 2001 in London. A brand new pedestrian bridge named Millennium Bridge opened to the public, stretching elegantly across the River Thames. It wasn't just functional, it was an architectural marvel. But there was a problem, a big problem. Within days of opening, the started swinging dramatically whenever people used it. And when pedestrians leaned to this way to steady themselves, things only got worse. The bridge began to twist so violently that it formed a giant S, essentially a horizontal shape. Engineers had to close it down for 2 years to fix the issue. So, what went wrong? Why did the engineers foresee this? The answer lies in a fascinating concept from physics: oscillations. So, oscillations describe any back and forth motion, the swinging of the pendulum, the vibration of guitar strings, and yes, the swaying of the Millennium Bridge are all examples. More specifically, the bridge's behavior was tied to a special kind of oscillation called simple harmonic motion. This is when the oscillation follows a regular, predictable pattern. Physicists often explain this using the classic example of a ball attached to a spring. Imagine the ball is lying still. That's its equilibrium position. Now, if you pull the ball to one side and let go, it bounces back and forth, oscillating forever in the frictionless world. This motion is the simplest example of how forces like elasticity and inertia interact. Now, let's dig deeper. What's happening to the energy in this oscillating ball? At its turning points, which is when the spring is fully compressed or stretched, the ball's kinetic energy drops to zero because it momentarily stops moving. Instead, all its energy becomes potential energy stored in the spring. As the ball moves back toward equilibrium, its potential energy transforms into kinetic energy. By the time it reaches the middle, its kinetic energy is at its maximum, while potential energy hits zero. So the total energy of the system remains consistent. It just shifts between forms. So, this interplay of energy explains how oscillations maintain their rhythm, whether it's in the spring or on a bridge. Now, let's return to the Millennium Bridge. The swaying started as a small oscillation, but it grew worse because of something called resonance. Resonance happens when the force is applied at just the right frequency to amplify an oscillation. It's like pushing a child on a swing. If you push at the right moment, the swing goes even higher. In the case of the Millennium Bridge, pedestrians unknowingly caused resonance. While as they leaned into the bridge's way, their movements matched its natural frequency, amplifying the oscillation until it became uncontrollable. So, what went wrong? The engineers who designed the bridge did account for oscillations, but only vertical oscillations. It's the kind that would make the bridge bounce up and down. They didn't predict the horizontal swaying caused by people walking. Initially, the swaying was barely noticeable, but as more people leaned into it, the resonance effect kicked in, amplifying the motion dramatically. Fixing the problem required adding damping mechanisms to counteract the oscillations, ensuring the bridge stayed safely. Interestingly, simple harmonic motion has a lot in common with uniform circular motion. Imagine a marble rolling in a perfect circle. If you look at the circle edge on, the marble appears to move back and forth along a straight line, just like a ball on a spring. So, the same math applies. The period of the motion depends on factors like mass and spring constant, or in the bridge case, the stiffness of the structure. Next, the frequency is simply the inverse of the period. And lastly, the angular velocity. It describes how quickly the oscillation completes its cycle. These shared properties make circular motion a useful analogy for understanding oscillations. So, the Millennium Beach fiasco was a costly but valuable lesson for the physics of oscillations and resonance. It showed that even small forces applied at the right frequency can cause massive effects. Today, the bridge stands firm thanks to engineering fixes informed by better understanding of oscillatory motion. And it serves as a reminder of the importance of considering all possible forces in design. So, next time you feel a structure sway, you know it's not magic, it's physics in action. Thanks for watching this video. Don't forget to like and subscribe and share the video. See you next time.